Welcome to Chem 4300. This is a course on physical chemistry, and I'm the instructor, Professor Philip Grandinetti. Here's my email address. Now, any course on physical chemistry could probably begin by asking this simple question. Will Newton's laws of physics work on the microscopic level? Can I describe the motion of atoms and molecules with the same type of physics that I use to describe motion that I see on human length scales, human time scales and length scales? Can I apply those Newtonian physics to describe the motion of atoms and molecules? Now, implicit in that question is the existence of atoms themselves, right? We know that idea goes back to the ancient Greeks, but experimentally, evidence for them didn't really show up until the 1700s or so, when chemists realized that there were substances that could not be further decomposed, and they identified those substances as elements. And what was important is that those elements always reacted in whole number ratios. And that was the clue that these elements were associated with discrete units of matter called atoms. And that's when Dalton proposed in 1807 the atomic theory of matter. Now, what we're interested in this course is how do we relate the motion of atoms and molecules to macroscopic properties? So we're interested in how we can take things like the volume, the density, temperature, pressure, viscosity, reaction rate, and relate that to what's happening on the microscopic level. Now, as you might imagine, when you think about a liter of water, that's a lot of water molecules, 10 to the 23rd water molecules or so. And describing every individual one of those water molecules' motion in terms of its trajectories, position, and momentum, and all of that is going to be impossible. But what was realized is that, well, we can still look at the statistics of all of these motions and relate a statistical description of what's happening to these macroscopic properties. This is what led to the birth of an area called statistical mechanics, which was developed from the mid-1800s to the early 1900s by people like Maxwell, Boltzmann, and Gibbs. And what they found was they could use all of the physics known at the time, and they could describe fairly well some of these macroscopic properties, but others not so well. And they couldn't really understand at the time why. They couldn't find any mistake in the way they set up their equations in this statistical mechanics, but for some reason they weren't getting the right answer in all the different situations, just a few of them. And of course, what they were missing was that there was no understanding of yet quantum mechanics. So it was around the turn of the 1900s that we understood that at the microscopic level that Newtonian physics don't apply, that we have to switch over to applying quantum mechanics. But when you do, then statistical mechanics, taking quantum mechanics into account, does now consistently give us connections between microscopic properties and macroscopic properties of materials. Now, what this course is about the quantum mechanics of atoms and molecules. So this is the way the course is organized. Now, you're going to have to learn about quantum physics and quantum physics as applied to atoms and molecules. Now, to get a good, deep working understanding of quantum physics, it's actually really important that you understand the classical physics that came before. Quantum mechanics doesn't invalidate this stuff. We still need to know all of this. It's going to build on top of all this classical physics, and then we're going to make it, we're going to use quantum physics to sort of take these equations and apply them on this side here in terms of quantum mechanics. So what we're going to do is we're going to go back through these concepts on how you might use classical physics to describe the translation, rotation, and vibrational motion of atoms and molecules. We'll see how it sometimes gives the right answer in terms of macroscopic properties, and sometimes it doesn't. And then we'll go to quantum physics and we'll learn about wave-particle duality and Schrödinger equation and wave mechanics. What's important to understand is that conceptually this is really quite challenging to wrap your head around all of this stuff. What makes it harder in some physical chemistry classes is that all of these concepts are introduced simultaneously with all of these concepts, and it's just conceptual overload. So I'm trying to sort of spread things out a bit and go back through all of these key important concepts first, and then we're going to move to quantum physics. And we'll go back through all of these topics, and eventually, when we look at their quantum analogs, we'll be able to describe all of that motion as that occurs in the quantum world, and we'll be able to eventually look at things like the structure of multi-electron atoms and diatomic molecules and all of that. Finally, in this course, we're also going to have to cover chemical kinetics as part of the syllabus. So we'll have the last 2 or 3 lectures covering some of that, although it's not going to be that really strongly connected to this other material. Now, for our purposes, we're going to begin back in 1686 when Isaac Newton published his Principia, and in his Principia, he gives us his 3 laws of motion. Before we get into those laws of motion, I think it's important that we sort of be clear about what we mean when we talk about a reference frame or a coordinate system that is used to define the location and orientation of objects. So we're going to be talking about reference frames that are inertial or non-inertial. So an inertial reference frame is any reference frame that's non-accelerating or non-rotating. So you might imagine that if you defined your reference frame as within the context of a seat on this roller coaster ride, then you're clearly in a frame that's accelerating and, in this picture, rotating. So if you define your reference frame from the point of view of a seat on this roller coaster car, then clearly you're in a non-inertial frame, right? On the other hand, let's say you're in this train and you're moving down the tracks at a pretty good speed, but in this case, you're moving straight and you're moving at a constant speed, so you're not in an accelerating frame, and in this picture we're going straight, so we're not in a rotating frame. So this is an example of an inertial frame. It's in a frame where it's not accelerating or non-rotating. Now you can imagine when the train is speeding up or slowing down or it's going around a turn, then it's no longer going to be an inertial frame. But if it's just going straight ahead at one constant speed, then that would be considered an inertial frame. Now, Newton's first law, what's called the law of inertia, says that if you're in an inertial frame, a particle either remains at rest or continues to move at a constant velocity unless it is acted on by a net external force. So in other words, an object in an inertial frame will not accelerate or decelerate at all when there are no external forces that are acting on it. Now, Newton's second law tells us that for any particle of mass m, that the net force is always equal to the mass times the particle's acceleration. So F equals ma. This is the sort of classic equation you learn in your high school physics. Now, more generally, we write this in terms of the particle's momentum vector. So the momentum vector is the mass times the velocity vector. And we write that Newton's law is that the force acting on the particle will cause a rate of change of the momentum vector for the particle. That is Newton's second law. So the force acting on a particle will change the direction and magnitude of the particle's momentum vector. Now let's consider a system of particles that we have. So in this case, I just drew 5 particles here and labeled them. If we were going to consider the force that's acting on any one particle, then we need to take then the forces, say in this case acting on the alpha particle, that it's going to be the external forces that are acting from outside onto this particle, and then the internal forces, which are the forces between each of these particles. So in this case, for say particle 5, there'll be internal forces of 1 on 5, 2 on 5, 3 on 5, and 4 on 5. So we'll represent that with this summation here. And we have a little notation here to tell us not to include particle 5 on 5. And that gives us the net force that's acting on particle alpha, right, in this example here. Now, if we want the total force acting on the system of particles, then we can take the momentum vector of every particle and do a vector sum to get the total momentum vector for all the particles. And then we can write Newton's law, which is force is equal to the rate of change of the momentum. So here we have the total momentum vector derivative, which is going to give us the total force that's acting on the particles. And we can write that with this expression here as the sum of the sum of the derivatives of the momentum vectors for each of the particles. and that's going to be just the sum of the net force on each of the particles from the previous slide, and then we can rewrite that again as the sum of the external forces on each particle plus the sum of all the internal forces here. So what we have now is an expression for the total force acting on the entire system. If I take that expression here and I look for Newton's third law, which tells us that if an object 1 exerts a force on object 2, then object 2 always exerts a force on object 1, which is equal and opposite to it. So Newton's third law tells us that this sum here, this double sum, is with this condition is going to cancel out to 0, and that the total force, the total rate of change, the rate of change of the total momentum is just going to be the sum of the external forces acting on the particles, or the we'll call the total external force acting on the system of particles. So with this definition then, what we see is that if there were no external forces acting on our particles, then the rate of change would be equal to 0, and the momentum, the total momentum of our system of particles, would be constant. This is what's called the principle of conservation of linear momentum. All right? So this is going to be true in classical mechanics, but will also be true in quantum mechanics, that if there's no external forces acting on our system of particles, then the linear momentum will remain constant. To give you an example of this in action here, here's an example where an astronaut is doing repairs outside her spaceship, and something happens and she gets disconnected from her tether line, and she's now floating out in space, out of arm's reach from the hatch door, and she needs to get back to the spaceship. So what does she do? She has a wrench in her hands, and she knows the conservation of linear momentum. So what she's able to do is to say, okay, if the hatch door is over there and I have a wrench, I can throw the wrench, and the linear momentum conservation will mean that as the wrench goes that way, I will have to go the opposite direction in order to maintain the linear momentum. So in this case then, we can write it this way, that the conservation momentum says that the initial momentum vector has got to be equal to the final momentum vector, which has got to be equal to some constant. So we're going to take the case where, so we'll write this out first of all as the mass of the astronaut times the initial velocity along the x direction. We'll put the whole problem along the x direction. The mass of the wrench times the velocity along the x direction is equal to the mass of the astronaut times the final velocity of the astronaut plus the mass of the wrench times the final velocity of the wrench is equal to a constant. And now, since we pick the initial condition where the astronaut and the wrench have 0 velocity, that means that this constant is just equal to 0 when you plug that into this initial condition here. So that gives us this expression here from this side for the sum of the momenta. So if we take that expression and rearrange it, we get that the final astronaut velocity is just going to be equal to the wrench's final velocity times the ratio of the mass of the wrench divided by the mass of the astronaut, with a negative sign there. So that's what we need then for the astronaut to move in the opposite direction that the wrench is thrown. All right, so this is just a quantitative example of how you can use linear momentum conservation. Okay, now another topic we want to talk about is whether the equations of motion for the center of mass. So this is actually a stroboscopic picture of a baton being thrown. So the baton is thrown in the air and it flips around, and what we're looking at is what the motion of just the center of mass of the baton is, and actually undergoes a very nice parabolic motion. And we can describe this with Newton's laws if we define the total mass of our collection of particles as capital M, and we define the center of mass as the weighted vector sum. So each particle's vector is weighted by its mass, and then those are summed up and then divided by the total mass. That defines what's called the center of mass of our collection of particles. So if we combine these two definitions with our Newton's expression for the total force is equal to the sum of the mass times the individual particles' accelerations, then we can obtain the equation of motion for the center of mass, which is that the total mass times the acceleration of the center of mass is equal to the force acting on the total system. Okay, so what we learn then is that if we take particles and we throw them in the air, they're going to execute some complicated motion, but the center of mass will just follow some simple parabolic path like a single particle would if it just had a mass of capital M. All right. So wherever the, if you imagine the baton is some distribution of masses here, the center of mass will then, as you throw it in the air, will just undergo this parabolic motion as if I just had a single particle thrown up with the total mass of the baton. So let's look at an example where we calculate the center of mass, say, of a water molecule. So we're going to take our distances here for OH, about 0.957 angstroms, and we'll take the HOH angles about 105 degrees, and we'll have the mass of the hydrogen oxygen in terms of atomic units, which is this definition here, which is 16 and 1. So in this picture then, what we're going to do is define a frame, and in this frame, we're going to place the water molecule in the ZX plane. So the water molecule have no coordinate along the Y, which is coming out of the board. And we're going to assume that all the mass is concentrated at the nucleus, so we can just place assume that the atoms are point masses, and we can just place them in this grid. We're going to put oxygen at the origin, and then with our orientation here, we're going to make it so that it's symmetrically positioned about the x-axis, so half the angle is above, half the angle is below. Now, with this positioning in our coordinate system here, then we know that the x-coordinate of the hydrogen atom is going to be d times the cosine of the angle divided by 2. So we're going to take this guy right here, divide 105 by 2, and the projection down onto this axis is going to be the x component. Similarly, for the z component, it's going to be plus or minus d times sine of that. So in other words, we're going to now do the projection. We're going to take this angle and we're going to project that way, and that's going to be plus or minus d times the sine of omega over 2. And so what we get for those three atom positions, well, of course, oxygen is at 0, but the hydrogen, first hydrogen is going to be a plus 0.526, and the other hydrogen is also going to be a plus 526 for x. But for the z, on the z-axis, the hydrogen atom is going to be, the first one will be a 0.57592, and the other one will be minus 0.7592. And so now we have all the Cartesian coordinates for this system, and we can go ahead and calculate the center of mass. Now, y is already 0 because there are no atoms off y equals 0. So for x, we'll find we just do this weighted sum here by the masses. So we take the mass of hydrogen 1 times its x position, the mass of hydrogen 2 times its x position, divided by the total mass, including the oxygen here, and that gives us this term here. Now, we didn't have to do for oxygen because it's 0 here, so that would have been in this sum, but that's 0, so we left it out. Similarly here for z, we do the same thing. So we have this equation here. So we place the mass of the first hydrogen times z, the mass of the second hydrogen times z. Oxygen is times 0, so it's not in this expression. We divide it by the total, and we get 0. So now for the position, we have z is equal to 0, y is equal to 0, and we have x off of 0 by 0.06473 angstroms. So if I go back to that picture that I had earlier, I can place this little dot here off the x-axis, as this dot represents the center of mass of the water molecule in this coordinate system. Okay. Now for the angular momentum vector, I'm going to use this lowercase script l symbol. And in physics, we know the angular momentum is defined as the cross product of the position vector and the linear momentum vector. So this is r cross p. In this diagram here, then we have from the origin out to the particle is r, and then p is the linear momentum of that particle. What's important to understand about this definition is that this definition depends on how you define your origin. if you had a different coordinate system with the origin somewhere else, you'd have a different angular momentum vector. So unlike linear momentum, which doesn't depend on the origin, angular momentum depends on the origin. And so that's something we're going to have to worry about as we go forward in this chapter. Now the rate of change of the angular momentum, which is dl dt, we can calculate from this expression, and it works out to be r cross dp dt. Now this isn't completely obvious from just looking at that expression, so check out the notes, online notes, to see how this is derived, but it's not so bad. Now this dp dt we recognize as the force that's applied to the particle. So the rate of change of the angular momentum vector with respect to time is r cross f. So that's what determines what changes the angular momentum. And that is defined in physics as what's called the torque. So the torque acting on the system changes an angular momentum. So if there was no torque acting on a system, then the angular momentum would stay constant. Okay. Now let's consider a system of particles and how the angular momentum would behave. And particularly we're interested in the total angular momentum. So the total angular momentum for this system we write as a vector sum of all the particles, and that we can write as the sum of the cross products of r and p for each particle. And the total change in the angular momentum, the rate of the change in the total angular momentum, dl dt, is going to be the sum of the change in the individual angular momentum, and we can write that as the sum of the cross product of r and dp dt, just like before. This guy we're going to recognize as the net force acting on the alpha particle. So now we have a system of particles, so there's going to be external forces acting on each of these particles, but there will also be internal forces on particles acting on each other. So remember that from the first chapter. So we take that expression and we write out that the net force here is the external force acting on each particle plus all the internal forces acting on that particle, so the interparticle forces. If we take that expression and we plug it into this expression, then this becomes two terms. The first term involves just the external forces on the alpha particle, so it's the sum of r cross f external. And then this guy becomes this double sum, which involves r cross all the internal forces. Now, what we learned in the first chapter is going to be true here. If you bring in Newton's third law, that the force of particle 1 on 2 is opposite in sign to particle 2 on 1, then you'll find that this double sum will go to 0, and we're left with the total change in the change in the total angular momentum is given by this sum of all these cross products of r with the external force on each particle. So given that expression then, the dl dt for the total angular momentum is the sum of all these cross products, and that's the sum of all the torques acting on each particle, the individual torques acting on each particle by the external force. Then that's what we call a total external torque acting on the system. And what's important here then is that the rate of change of the total angular momentum is the total torque, and if the total torque is 0, then the total angular momentum will remain constant. In other words, if total torque is 0, dl dt has to be equal to 0, and that means that the total angular momentum remains constant. This is the principle of the conservation of angular momentum. So an analogy to what we saw in the first chapter, the principle of conservation of linear momentum, if there was no force acting on a system of particles, the linear momentum remained constant. Here we see if there's no torque acting on a system of particles, the angular momentum, total angular momentum, will remain constant. And so this will be true also in quantum mechanics, as we just saw that was true in classical mechanics. Okay, let's continue with this exploration of angular momentum and look at a way we can divide up the angular momentum in the system of particles. So in our system of particles, we have the total angular momentum, and I'm going to write it as the vector sum of all the individual angular momenta, but I'm also going to write this sum of the cross product of the position vector with the momentum. I'm going to break the momentum up into the mass times the velocity vector here. And the reason I'm doing that is because what I'm going to do is I'm going to take my system of particles, just like we did in the first chapter, and we're going to define the center of mass for that system of particles. And then we're going to define the center of mass vector and a vector from the center of mass out to each of the particles. So I'm going to write the position vector in my coordinate system as the sum of the center of mass vector plus the position vector relative to the center of mass. So this sum here, I'm going to take and I'm going to plug that into this expression up here and expand this out. And what we're going to find is that the total angular momentum can be written as two terms. One is just the cross product of the center of mass vector with the total linear momentum of the system of particles. And the second term is the sum of all the position vectors relative to the center of mass cross product with the momentum vector defined with the position rate of change of the position vector relative to the center of mass. So that means that we can take this expression here and describe the total angular momentum of our system, and we're going to redefine this guy as something we call the orbital angular momentum, and this guy we're going to define as what's called the spin angular momentum. So these two components, this is going to be like the angular momentum associated with the Earth going around the sun, for example, whereas the spin angular momentum would be associated with the Earth spinning about its axis. So these two terms we're going to be using also when we get to quantum mechanics, but this is also true in classical mechanics, and it's a very convenient separation by moving into a coordinate system associated with the center of mass of your system of particles. And so what's also true is that when the total angular momentum is conserved, you might find there are many cases where you can approximately find that the orbital angular momentum is conserved separately and spin angular momentum is conserved separately. So in other words, if dl dt is equal to 0, you might find that dl orbital dt is equal to 0, approximately equal to 0, and dl spin dt is approximately equal to 0 too. And sometimes that happens.